November 2023, paper 6, variant 3. In question 1, you have sand, which is a granular material, right? Composed of very small, irregularly shaped mineral particles. Anyway, we need to find the density of this sand. So first method, we found the mass of the sand. Can I find the mass based on these two readings? Yes, I can. 219 minus 76. What's 219 minus 76? This is 143 grams. This is the mass of the sand inside the mm, inside the measuring cylinder. And then the volume of this sand was 108. Can I find the density? Yes. So it's 108 I'm sorry, 143 divided by 143 divided by 108, which is 1.32. Do not forget the unit, grams per centimeters cubed. Not bad. Method 2. Method 1, he just added the sand, he found the volume and the mass. In method 2, he added water, right? He pours 100 centimeters cubed of water into the measuring cylinder containing this sample of sand. Can I find volume 2 of the water? Yes, I can find volume 2 of the water, as we all said, from the bottom of the meniscus. From the bottom of the meniscus. So this reading over here, okay, this reading is what? Is 154. Okay, take the reading from the bottom of the meniscus. 154. Why? Because if you take this reading, this is wrong. This is 156. It is wrong. So the volume is 154 centimeters cubed. Calculate another value for the density rho 2, in which the mass, okay, the mass, the initial m, which was 143, 143 divided by v2 minus k, v2 which is 154 minus k which is 100, right? So rho 2, density 2 would be 2.65. Again, do not forget the unit, grams per centimeter cubed. Okay? Okay. Now we have figure 1.4. Draw an arrow to show the correct line of sight. Line of sight perpendicular from the bottom of the meniscus. So you'll draw a line of sight perpendicular from the bottom of the meniscus. Okay, with an eye. This is the arrow. Okay, you can be pointing to this. It has to be perpendicular. Now that the student wants to determine the density of the particles in a similar sample of sand. Explain why method 1 would not be a suitable method for him to use. You have sand and he wants to measure or he wants to calculate the density, right, of the particles. How can I find the density of the particles of the sand? Again, you need to find the mass and the volume. But the problem with the sand is what? As he stated in the beginning of the question, he said what? That the sand is composed of very small, irregularly shaped mineral particles, right? So these very small particles aren't exactly touching or aren't exactly filling up the whole volume, right? The volume of the sand in this question in part A in method 1, the volume was 108, wasn't it? Yes, it was. Is this the actual volume of the sand? No, it's not the actual volume of the sand. Why? Because if you talk on a very small level, talking on a particle level, does it actually fill up this whole space? No. There is actually a lot of gas molecules. There's a lot of air inside this, okay, inside this volume. So air actually makes up a lot of this volume. It's not pure sand. It's not pure sand. So for this question, you need to say that the volume, okay, is actually larger. Why? Because due to the air, okay, between the grains, the volume is larger than the sand, and then the sand alone. Why? Due to air between the particles. or the sand grains or whatever. Explain why method 2 would give a more accurate value for the density of the particles. In method 2, what did he do? In method 2, he added water, right? He added water to the sample. So why is this a more accurate value? Because the water fills up the volume. The water comes in between these sand particles. Okay? Water, okay, it fills up the volume completely. It doesn't allow any air molecules to be there, just displaces them, right? Okay, describe two possible sources of inaccuracies taken in method 1 or method 2. Method 1 or method 2. For example, in method 1, if you take a look at the volume of the sand, is the surface horizontal? It's not horizontal, right? It's not flat. So this is one possible source of inaccuracy. Surface in method 1. Okay. The surface in method 1 isn't flat. Okay. What other source of inaccuracy? For example, if we take a reading, if we take the reading of this volume was 154. The graduations here are a bit too large. Saying you keep on increasing by 2 centimeters cubed, right? You keep on increasing by 2 centimeters cubed. Is this sufficient? No. A smaller, an actual smaller graduation might be a lot more accurate. Graduations are too far apart in method 2. The graduations in the measuring cylinder, okay, in the measuring cylinder are too far apart or are too large. Okay. Now, moving on to question 2. You have a lid, you have beaker A, okay, and you have beaker B, right? You have beaker A and you have beaker B. Hmm. The student investigates the cooling of hot water in surroundings with different temperatures. He uses the apparatus shown. Student pours 100 centimeters cubed of cold water into beaker B. This is cold water, right? Cold water. Measure and record an appropriate column heading, in the appropriate column heading, the temperature theta 1 of the water shown in figure 2.1. So this is the initial temperature of the water shown in this figure, which is 18 degrees Celsius. Can I write it down in the table? 18 degrees Celsius. This is the initial temperature of the cold water, right? Student places beaker A inside beaker B as shown in figure 2.3, so that the water in beaker B rises between the sides of the two beakers. He removes the lid and pours 150 centimeters cubed of hot water into beaker A. So now beaker A, right? Beaker A has hot water. He records the temperature every 30 seconds. Describe one precaution. Take the reading perpendicularly to avoid the parallax error. Take the reading, okay, perpendicularly to avoid the parallax error. And then we have the table, 18 degrees Celsius, 48 degrees Celsius. Write a conclusion stating in what way the temperature of the surrounding beaker A, okay, of the water in the surrounding beaker A, affects the rate of cooling of the hot water in beaker A. You have in warm water and you have in cold water. First experiment, he added the water in, he added beaker A, which has hot water. It has hot water. Beaker A has hot water. Okay. If you add this hot water into another beaker which has cold water, and if you add this into a beaker which has hot water, would this affect the rate of cooling? Well, we'll see. First of all, at zero, it was 78.5. It decreased all the way to 62, which is a difference of 16.5, right? 16.5 degrees. On the second experiment, it was 80, decreased all the way to 70. So this is a difference of only 10 degrees. Does it affect? Yes, it does affect. So as the temperature increases, okay, as the temperature of the water or of the, let's say, the surrounding water, instead of just saying the water, um, of the surrounding beaker, of the water in the surrounding beaker uh, increases, the rate of cooling decreases, right? How does it decrease? Okay, how does it decrease? If it was 18 degrees Celsius, if it was, okay, 18 degrees Celsius, what happened? It started off at 78.5 minus 62, which has a difference of 16.5 degrees Celsius, right? What about if the temperature increased to 48 degrees Celsius? Gave you a difference of 80 minus 70, mm, only 10 degrees Celsius, right? Only 10 degrees Celsius. Can I find the average rate of cooling cooled water in cold water? Can I find the average rate of cooling in cold water? Theta A 0 and A 180, which is 78.5 minus 62 divided by 180. Minus 62 divided by 180. This would give you a rate of 0.0917 or 0.092. Do not forget the unit, which is degrees Celsius per second. Degrees Celsius per second. Hmm. Another student repeats this experiment at the same room temperature. State two other variables that she controls. What are two other variables that she controls? She has to control the volume and the initial temperature. The volume of the water and the initial temperature of the water. Hmm. After 180 seconds, student measures the temperature of the water surrounding the beaker A in the first experiment and finds that theta 1 is 49 degrees Celsius, right? After 180 seconds, she measures the temperature of the water surrounding beaker A in the first experiment. State the reason why this can affect the results of the investigation and suggest what effect it has on the value of the cooling rate R. So surrounding water is now 49 degrees Celsius. Okay, isn't it higher? Isn't it much larger than theta 2 at the end? Isn't it much larger? Theta 2, what was theta 2? Okay, so theta 2 was 48. Okay, and 49 is actually larger than theta 2. Yes, it is much larger than theta 2. This means, okay, this means that this would affect the rate of cooling. Okay, it's much larger. Theta, okay, is larger. Okay, the temperature is larger. It's larger than theta 2, right? It is much larger than theta 2. How does this affect the rate of cooling? If you have a larger R, if you have a larger final temperature, how would this affect the value of the rate of cooling? Well, this would decrease the value of the rate of cooling, right? It would decrease the rate of cooling decreases. Okay, rate of cooling uh, decreases. That's it. Rate of cooling decreases. Hmm. Now, suggest one change to the experiment to reduce this effect. How can I reduce this effect? Yes, by using a constant temperature, for example, or yeah, decreasing by using a larger temperature, a constant temperature, a constant temperature. for the surrounding water. In question 3, you have the distance u between the illuminated object, which is 20 centimeters. She moves the screen until a sharp image appears. Describe a technique to obtain the image that is as sharp as possible. What is the technique to obtain a sharp image on the screen? We know the technique. Move the screen slowly back and forth, right? Move the screen slowly back and forth. Back and forth, right? Student repeats the procedure for 30, 40, and 50. Can I find u over v for this question? Yes, u over v would be 20 divided by 60, 0.33. Plot a graph of u on the y-axis, u slash centimeters on the y-axis, and u slash v on the x-axis, u slash v on the x-axis, and he already said that you have to start from the origin. He placed the origin 0 and 0. Draw the best fit line. So u 20, 30, 40, you have to say 10, 20, 30, 40, 50, and 60, right? And then for u slash v, it's all the way up to 3, 5, 1, 2, so it's 0.5, 0.5, 1.0, 1.5, 2.0, 2.5, and 3.0. 20 with 0.33. Okay, let me zoom in a little. 20 and 0.33, where is 0.33? So this is 3. So it's all over here. This is 20 and 0.33. 30 and 1.1. 1.1, right? 40, 1.55. 1.55. So it's over here. 50, 2.34, 2.3, zoom out. Okay, 2.25, 2.3, 2.34. It's over here. 50 and 2.34. And last but not least, 60 and 3. Right? I'll draw the line and then determine the value when u over v slash is equal to 0. Okay, so drawing the line and finding the slope. Okay, so you have 2 points above. Okay, or basically 1 point above and 1 point below. Yeah, this might be a really good representation of the line. What was the value, okay, of u slash v when, so the value is 15. Value is 15 at this point. It is 15. And then can I find the gradient? Yes, I can find the gradient. Y2 minus y1 over x2 minus x1, but you have to draw the triangle method. Okay, I'll have to draw the triangle method. Okay. Again, if your value is slightly above 15, slightly below, it's okay. So 16, 17, yes. 14, 13 might be acceptable. Do not worry. This is the triangle method, y2 minus y1 over x2 minus x1. So what's 60? What's 60 minus 20? I'll take the values from the table. It's okay. Over 3 minus 0.33. 14.98 or 15. Okay, 14.98 or 15. Let me remove this line. So the slope is what? The slope is 15 as well. Okay, so just one precaution that can be taken to ensure the measurements are as accurate as possible. One precaution, what was this experiment? You had the lens, so use a dark room. Use a dark room, right? Hmm. And now, moving on to question 4. Plan an experiment to investigate how the intensity of the light produced by the lamp is affected by the current in the lamp. You have lamp. Okay, plan an experiment to investigate how the intensity produced affects the current. Intensity, you have this light meter. What is this light meter? It measures the intensity of the light, right? It measures the intensity of the light. Plan experiment. The apparatus available. You have the lamp, the power supply, the light meter, okay, an ammeter, a variable resistor. A variable resistor. Complete the circuit to show the variable resistor connected to control the current. So you have to draw the variable resistor. Okay, you need to draw the variable resistor series this way, right? So this is my variable resistor. And then the key variables. What am I changing? First of all, what am I changing? What is the plan experiment to investigate how the intensity is changed or is affected by the current, right? So the variable, the control, the independent variable is what? Independent variable is the current, right? Range of values. Okay, the range of values is the current. We can give several values for the current. So, for example, 1 ampere, 2, 3, 4, and 5 amps. You have the current in the circuit, right? What are the key variables? What are the key variables in this question? Key variables, if you think about it, don't have that many actually, don't have that many key variables. But one of the most important key variables would be the distance between the lamp and this device and this light meter, right? The distance between the lamp and the light meter has to be constant. So the controlled variables, controlled variables, you have to have the constant distance, okay, the distance, okay, between the lamp and the light meter. It has to be constant. Okay, he does not need me to write down any extra apparatuses. No, how can I briefly conduct this experiment? So the steps to conduct this experiment would be quite easy. The steps change, okay? Change the resistance of the variable resistor, the variable resistor for each, okay, for each resistance, for each resistance, measure or find the current, okay, and take the reading of the light intensity, okay, intensity from the light meter, right? From the light meter. You keep on changing the variable resistor, and then you measure the current and take the reading of the current from the ammeter, okay? And then measure or take the reading of the light intensity from the light meter and repeat for different values of resistance and current, right? Repeat for different, okay, values of resistance and current. Okay, good. So these are the steps. Can I draw a table? Yes, I can draw the table, and then uh, repeat or write down the conclusion of the table. If you want to draw it here in this empty space, table would include not much, to be honest. Okay, what is the thing that I'm changing? Hmm. I'm changing the current, right? You're changing the current. And based on it, you have the light intensity. So the current in amps and the light intensity. Should I write down a unit for the light intensity? Nope. Light intensity. And then for the conclusion, okay, for the conclusion, I'd say for each value of current, repeat the experiment, repeat the experiment, and take average. Record the readings in the table. Record the readings in the table. And last but not least, compare the results. Okay, compare the by drawing a graph or by plotting a graph. Okay, a graph of the independent versus the dependent variable of the current versus the light intensity. Okay,